think about where we are in this course right now. Way back in January, we said there are these things called electric charges. Electric charges imply the existence of this type of vector field called the electric field. Later on, we learned that moving charges imply the existence of a different type of vector field called the magnetic field. So, in a way, we could think of electric charges as being the source of an electric field and electric currents being the source of a magnetic field. We then ask the question, is it possible for electric or magnetic fields to exist in the absence of any source? So, could we have some type of E and B other than zero for a region where there is no charges and no currents present? And what we found was the answer to that question is yes. The solution to a source free electric and magnetic field would be a wave equation. So we interpret these propagating electric and magnetic fields as light. So what we did is we took the Maxwell equations, the four equations that underlie all of electricity and magnetism, and from them we were able to predict the existence of a propagating electromagnetic field. So what we did was we just took what we know of the behavior of electricity and magnetism and we predicted the existence of light without assuming anything about it. And we found that the speed of light is based on two constants of nature, this epsilon naught and mu naught that we've been talking about for a while now. So if we're talking about waves, let's just talk about waves for in general and what is a wave. So very often a wave is going to be drawn to look something like this. In the purest sense, a wave is a thing that is infinitely long. One important property of a wave is known as the wavelength. Wavelength is designated by a lowercase Greek letter lambda, and wavelength is the distance from peak to peak. So wavelength would be something we just measure in meters, or nanometers, or kilometers, or whatever other measurement you're using, depending on what type of wave you're working with. Another important property of a wave is what's known as frequency. So frequency is given by the lowercase letter f, and frequency is the number of cycles per second. Frequency would be measured in units of 1 over seconds or inverse seconds, and inverse seconds is given the SI unit of hertz. So intuitively, what is frequency? Wavelength, okay, I could have a good visualization of that as something I measure with a meter stick. How should I be thinking about frequency? Well, a wave is a moving thing, so let's suppose the wave is moving to the right. And if you are watching the wave approach you, you could ask the question, if you're just standing still, you're watching the wave approach you, how many peaks will pass by you every second? Basically, that is asking the question, what is the frequency of this wave? If you see 10 peaks pass by you every second, then you would say the wave has a frequency of 10 hertz. So the wave is drawn like this, but we have something on the horizontal, we have a position. What's the vertical scale of this plot? The wave is going between a maximum value and a minimum value. The wave averages at zero, but what is the wave? Well, that depends what type of wave you're talking about. If we're talking about a water wave, the vertical scale could be wave height. So the top of the wave could be the peak up here. The trough of the wave could be the bottom down there. If we're talking about a sound wave is alternating regions of high pressure and low pressure in the air. So if you have a lot of air molecules packed together, that you would have a higher than average air pressure. That would be like a peak. If you have air molecules that are more dilute and spread out, you would have a trough. If you are talking about a light wave, the vertical scale could be the relative strength and direction of the electric field or magnetic field, if you wish. If you're talking about the wave, the vertical scale could be the average number of people standing at a given time. So waves also move. A wave's speed is given by lambda times f. So the speed of a wave is the wavelength times the frequency. So here's an animation of an electromagnetic wave. In an electromagnetic wave, the direction of the electric field and the direction of the magnetic field are always perpendicular to each other, and the direction that the wave moves is perpendicular to both E and B. So in this picture, the wave is traveling in the X direction, the electric field is pointed in the Y direction, and the magnetic field is pointing in the Z direction, either positive or negative Y and positive or negative Z. Now, in this animation, the electric field is drawn to extend upward into the y-axis, either positive or negative, and the magnetic field B is drawn to extend into the z-axis, positive or negative. Technically speaking, this wave of light only exists along the x-axis. So the wave of light does not exist anywhere off the x-axis. The wave of light does not exist anywhere other than y equals 0 and z equals 0. Just if you are going to draw a picture of a wave artistically, you will want to represent a strong electric field compared to a weaker electric field, so you will draw the electric field extending up into the y-axis above and below. Sometimes it'll be bigger, sometimes it'll be smaller, and that's fine. So in this picture, E and B are drawn extending off the x-axis, but in reality, this is just because we want to artistically represent the relative strength of E and B. As I said, the light wave itself is traveling along the x-axis and is only located at y and z are both equal to 0. So we have a propagating electric and magnetic field that we call light. We have the speed of this wave given by this value. The speed of light is often designated by the letter c, and we have 1 over square root mu naught epsilon naught. So why is this result really interesting? Let's consider this thought experiment. Let's suppose a universe that's completely empty except for you. You have your spaceship, you have your lab equipment to do some physics experiments with. So here you are with your spaceship and all your lab equipment that you could ever want. Now you will be interested in electricity and magnetism. You discover the Maxwell equations and you do some experiments to determine the actual value of epsilon naught and mu naught. And when you learn about the Maxwell equations, you discover there is this propagating electromagnetic wave, and this propagating electromagnetic wave travels at a speed of 1 over square root mu naught epsilon naught. And so you plug those numbers into a calculator. So you find the speed at which this light wave propagates is 3 times 10 to the 8 meters per second. Now, in this thought experiment, the universe is completely empty except for everything in your spaceship plus you. Let's consider a different observer that is really far away from you for the moment. They have their spaceship, they are really far away, they do not know the existence of you. They do their physics experiments and they learn about the Maxwell equations as well, because this is how nature works. So they learn about them and they learn how electric and magnetic fields fill the vacuum, and they find a value for epsilon naught and mu naught that is the same value as what you find. So they then later on use the Maxwell equations to predict the existence of a propagating electromagnetic wave, and they interpret that electromagnetic wave to be light, and they determine that these electromagnetic waves travel at 3 times 10 to the 8 meters per second. Now, if nothing else exists in the universe other than you have no reference to compare your motion to. So for all practical purposes, you could consider yourself to be perfectly at rest, and that is a perfectly valid outlook to take. But then let's say at some point, way off in the distance, you see that other spaceship, and the other spaceship is just drifting towards you. It's not speeding up or slowing down. It's just moving relative to you. You both have your engines turned off. So Rick and Morty's spaceship see the Planet Express spaceship moving by with some velocity v. Now Rick and Morty know their engines are turned off, and they know that they measured these fundamental constants of nature and they got values for them. Simultaneously, The Planet Express, they know their engines are turned off, so from their perspective, Rick and Morty's spaceship is just drifting by them with a constant speed of v, and they're moving to the left at that same speed. Now, on the Planet Express, they did their experiments and they found the values of epsilon naught and mu naught. Both perspectives are perfectly okay to be regarded as correct. If you want, you could imagine Rick and Morty are at rest and the Planet Express ship is drifting by at constant speed. Or you could imagine the Planet Express is at rest and Rick and Morty are just drifting by at constant speed. If no one is accelerating, then both perspectives must be valid. Now, both spaceships did their experiments on how charges move around in vacuum and how electric and magnetic fields propagate through the vacuum. Both spaceships determined the same value of epsilon naught and mu naught. So neither perspective is going to be preferred by nature. Both ships will measure the same properties of the vacuum. Both ships agree on the value of epsilon naught and mu naught. And both ships discovered these propagating electromagnetic waves. And both ships discovered the relationship between epsilon naught, mu naught, and the speed of these propagating electromagnetic waves. So if both spaceships measure the same values of epsilon naught and mu naught, both spaceships will measure the same speed at which these waves travel, 3 times 10 to the 8 meters per second. So the speed of light is going to be the same to both observers, even if those observers are moving relative to each other. And this actually leads to a very profound consequence. The speed of light is the same to all observers. So no matter how you're moving, whether you're stationary or moving relative to somebody else, you will always measure the same speed of light. You will always measure light to move at 3 times 10 to the 8 meters per second. So let's suppose you have 2 observers, and for this thought experiment, let's suppose Rick and Morty's ship is at rest and the Planet Express is moving to the right at 2 times 10 to the 8 meters per second. And then let's suppose we have 3 photons moving away from them, 1 photon moving towards them. The Planet Express would see 1 photon traveling towards them and 3 photons traveling away from them at a speed of 3 times 10 to the 8 meters per second. Rick and Morty would see the exact same thing. They would see 1 photon traveling towards them and 3 photons traveling away from them at 3 times 10 to the 8 meters per second. Even though these 2 observers have different speeds relative to each other, they still see the particles of light moving at the same rate. So the speed of light through a vacuum is determined by constants of nature. Your motion does not affect the value of these constants of nature, so your motion will not affect what you measure to be the speed of light. In classical physics, we always assume that the rate at which time passes and the length measurements we make are always going to be the same to all observers. Now, in reality, this is not really the way nature works. If the speed of light is fundamentally the same to all observers, regardless of how those observers are moving, what happens is length measurements and the rate at which time passes by ends up becoming dependent on the observer's relative motion. So the length measurements and the rate of how time passes depends on who is measuring those quantities. Now, this result is not intuitive to us, and the reason for that is, as a rule of thumb, if you're not moving faster than about 10% the speed of light, very often these effects become very negligible. So only when you're moving super fast do these effects become very important. But regardless, this is the way nature works, and we are not given a handbook or a user manual to figure out how nature works. We are just here, and it is our job to try to determine the rules of nature while living within nature. So, electric and magnetic fields may propagate through space without the presence of any source at all. And these electromagnetic waves are what we observe as light. Now, there are different colors of light. There are some colors of light we can see with our eyes. there are a whole lot of other colors that we cannot see with our eyes. Wavelength or frequency are just colors of light that we cannot see. Now, red and orange and green and violet, these are just broad generalizations for the notion of color. If I want a proper quantitative way to describe color, I would use wavelength because then I could talk about the difference between 638 and 640 nanometers rather than say red and a little more red. Now, indirectly, we can detect infrared radiation as well. We detect it as heat. It's not as exciting as the colors we could detect with our eyes, but as I said, there are a whole lot of colors of light that we just cannot see with our eyes, but they are colors of light, radio and X-ray and infrared. They are just as valid of colors just as red and violet and blue are. Now, the speed of light itself is often referred to as a universal speed limit. The statement here is true, but this is not the most accurate statement we could make. A better statement to make is light travels at the speed of causality, or in other words, light travels at the speed of gravity. So, what do I mean by light travels at the speed of causality? Before I get into that, I am going to claim that nature should probably not allow the existence of a paradox. I am not going to attempt to prove this statement. I think this is a very reasonable thing to expect in terms of the way nature behaves. Let's suppose we do some science and we think we discover a paradox. If we think we come across a paradox somewhere in life, then I'm going to claim that one of the following must be true. Perhaps there are some underlying rules of physics, some underlying rules of the way in which nature works that we don't really understand. So it's not that there's a paradox, it's just there are physics going on that we don't really know what's going on. Maybe it's doubly special relativity or super duper symmetry or something like that. Maybe we have made a mistake. Somehow we have not properly taken into account the physics of what's going on. And again, it's not that there's a paradox, we're just doing something wrong, and if we were to properly take into account all the relevant physics, then the paradox would go away. Or maybe we did discover a paradox, but that would be sounds like it would be saying we discovered an incident of the universe being inherently illogical. We discovered that A is not equal to A. And I think in most logic classes that would not be allowed. So we're going to assume that's not the case. So, what do I mean by the speed of causality? Well, first let's talk about causality. So, if light travels at the speed of causality, let's consider two events that are related to each other. So, how about we have a really exciting 51-yard touchdown pass where the quarterback throws the ball and the receiver catches it, and after the quarterback throws the ball here and the receiver comes down and catches it, the crowd goes wild. These are two events, but these events are very clearly correlated with each other. If you were in the stadium watching this game, you would say that the touchdown pass was thrown and then the crowd went crazy. Maybe you were watching this game from somewhere else. Maybe you were in a really tall building downtown and you would still observe the same progression of events. You would see the touchdown pass be thrown, and then you would see the crowd go the appropriate magnitude of nuts. These are two different events. We would say the 51-yard touchdown pass occurs, and then the crowd goes wild. So in a way, you could think of that as saying the touchdown pass, the fact that the ball was caught, affected the crowd's reaction. If the ball happened to be dropped, then the crowd would not be cheering like crazy after this play. We want to demand that every possible observer will see the same order of these events. So in other words, you will never be able to observe the crowd go wild and then the pass be thrown. So it doesn't matter where in the universe you are watching this game from. You might be watching this game from the stadium, from a building downtown, maybe you're watching it somewhere from the Andromeda Galaxy, you should always see the same progression of events. You should always see the crowd's reaction occur after the result of the play is known, after the ball is caught. It's possible also you are a moving observer. If you're just sitting in the stadium watching, well, then you're at rest relative to the field. But if you are maybe flying in a blimp overhead, or maybe you're accelerating through space in a spaceship going around the black hole at the center of our galaxy, you should still always observe the touchdown pass be thrown first, and then you should see the crowd's reaction and the cheering. So it doesn't matter where in the universe you are watching, it doesn't matter whether or not you are moving relative to the game, you should always see the crowd's reaction occur after the pass is caught. So we could generalize this concept. Let's suppose we have two events, A and B, and let's redefine if event A is able to influence event B, but not vice versa. It is possible to prove that there is a maximum speed for any moving object, and that is what we define as the speed of causality. So, in other words, if we require cause always comes before effect from the point of view of every possible observer, the universe will possess a maximum speed. And this is the speed that light and other massless particles travel at. Now, this conclusion that requiring cause coming after effect implies the existence of a maximum speed limit to the universe. This conclusion is definitely not obvious. The proof is beyond the scope of this course. If you're curious to see an academic paper where this relationship is proven, here's a link to this paper. But I think it's very reasonable to say if the universe is to make sense, if the universe is to be inherently logical, we should always require cause to come before effect. And light, being a massless particle, light travels at the maximum possible speed, so light will travel at the speed of causality. And I think causality is more fundamental to a universe that makes sense than the existence of electric charges and the Maxwell equations. So, Io. Io's a really neat place. Io's a moon of Jupiter. It's a little bit bigger than our moon, but not by that much. It has the same color as a pizza. It also has the least water of any object in the solar system, and it's the most geologically active object in our solar system. So here's an example of Io was seen by the Galileo space probe in 1999, took a picture there, and then New Horizons 8 years later on its way to Pluto took a picture, and you could see the surface of Io has evolved since then. So Io also orbits Jupiter in 42.46 hours. So why is Io going to be interesting to us? The speed of light was first measured quantitatively in 1676. And the way the speed of light was measured was using the moon of Jupiter, Io. So how could you measure the speed of light? Galileo, other scientists tried to ask the question, does light travel infinitely fast, or does light just travel really, really fast, but not infinitely fast? And they tried to have explosions and mirrors that were far apart from each other, and they could not really determine this. Now, today we know there is a limit to the speed of light. Light does not travel infinitely fast, but light travels so fast that this was beyond the capability of what some really brilliant minds of the past were able to measure. So, how did they use the moon Io to measure the speed of light? So here's the orbit of Earth going around the sun. Jupiter is 5.2 times further from the sun than Earth. So here's the orbit of Jupiter, 5.2-ish times further away from the sun. And here's the orbit of Io going around the sun. Now the sun shines on Jupiter. Jupiter casts a shadow. So Io is sometimes going to be in the shadow of Jupiter as it passes behind the planet. Now, if the speed of light is infinite, the time that Io will emerge from out of Jupiter's shadow to the next time Io emerges out of Jupiter's shadow will always be the same. So if Io takes 42.46 hours to go around Jupiter once, we should always see Io emerge from Jupiter's shadow every 42.46 hours. If the speed of light is not infinite, then the time we see Io to emerge from out of Jupiter's shadow will be a little bit more or a little bit less than this 42.46 hours. And the reason for that is while Io orbits Jupiter, the Earth is moving in its orbit. Technically, Jupiter is moving in its orbit too, but Jupiter is far away. It moves much slower than the Earth does around the Sun. So we'll assume Jupiter to be stationary and we'll assume the Earth to be orbiting the Sun. And so if Io emerges out of Jupiter's shadow, the light comes from Io and the light will hit the Earth right here. And then in 42.46 hours, Io is going to orbit Jupiter once more. Io will emerge out of the shadow. The moment Io emerges out of the shadow, you could see it coming out of that shadow. But in that time, the Earth moved a little bit closer. So the light has a little bit less distance to travel in however far the Earth moves in its orbit 42.46 hours later. And so in this case, we'll see Io emerge out of Jupiter's shadow in a little bit less than 42.46 hours. And if the Earth is moving away from Jupiter, then you would see Io emerge from behind Jupiter, from Jupiter's shadow, a little bit longer than 42.46 hours. And this measurement of the speed of light, it was performed in 1676, and it was only by about 20% off. So this was actually an incredibly precise measurement for a fundamental constant of nature, the speed at which cause is guaranteed to occur before effect. Io attacking its city with lightning. We said in chapter 17 that if you were to take two capacitor plates and you charge up the capacitor, that capacitor could store energy. Now, the place where that energy is stored is in the electric field between the plates. If that energy is stored in some volume, we could meaningfully talk about the notion of an energy density, the amount of energy per unit volume stored. And that energy, as we said, is stored in an electric field. So the energy density is given as 1/2 epsilon naught E squared. Now, energy density is usually designated by lowercase u, and I have this E to designate the energy density stored in an electric field. Similarly, a magnetic field could store energy, and the energy density stored in a magnetic field is given as 1/2 B squared over mu naught. Light itself will carry energy. So every photon, every particle of light has some amount of energy, and that particle of light will carry some amount of momentum with it. So the energy of a photon and the momentum of a photon are related by E equals PC. This subscript gamma is just there to designate we're talking about a photon. So this is really energy equals momentum times the speed of light, and this equation in particular applies when the particle that is moving is massless. So for the case of a particle like a photon. Now, remember last semester when we talked about momentum, a very important concept on the topic of momentum is the notion of momentum conservation. So let's consider an object that is initially at rest, and that object is going to absorb a photon. So this problem is identical to two cars that collide where one car is at rest, another car slides into it, and then they both will move off together because momentum is conserved. So here we have a cabbage that is not moving, so we could say the cabbage's initial momentum is 0, and we have a photon with a momentum E over C. Now, this is before the collision. After the collision, the cabbage absorbed the photon's momentum. Because the total initial momentum is E over C plus 0, I know the total final momentum must also be E over C. And if I set E over C, the initial energy of the photon divided by the speed of light is equal to mv, I could use that to find the final momentum of the cabbage, and hence the cabbage's final speed. Let's consider a different scenario. Let's consider where the photon is reflected rather than absorbed. So here we have a mirror, and let's suppose the mirror is not moving, so it has an initial momentum of 0. The photon again comes in with a momentum of E over c. Now, after the collision, the photon is going to be reflected back because this is a mirror and mirrors reflect things back. So the initial momentum of the photon was E over c in the positive x direction. The final momentum of the photon is negative E over c because the photon is now moving in the negative x direction. That's why there's this negative sign here. Well, if momentum is to be conserved, then whatever the photon's final momentum plus the final momentum of the mirror must add up to the initial momentum in total. So from that, I could infer that the final momentum of the mirror will be 2e over c, because the total initial momentum must equal the total final momentum. Last semester, we also talked about impulse. Impulse is the force exerted over a very short time interval, like the forces that are present during a collision. Impulse causes a change in momentum. Pressure is a force that is applied over an area. So the pressure is equal to the force on an object over the area that is being pushed on by that force. On the previous two slides, we saw that when a photon collides with an object that is initially at rest, that object will experience some change in momentum. That object will experience a delta p, and hence there will be a force from the photon, there will be an impulse from the photon. So if the photon is absorbed by the object's change in momentum is going to be delta p equals E over c. If the photon is reflected by the object, we get a different change in momentum. The change in momentum of the object is 2e over c. So if we combine the equations for impulse and pressure, we find we'll begin with pressure is equal to force over area. On the previous slide, we said, okay, pressure, force, here's force right here. So I could write pressure is equal to 1 over area, impulse divided by delta t. And if I replace impulse with delta p, I could say the pressure is 1 over area, delta p over delta t. Now notice that the pressure on an object that is being hit by a photon, in other words, the pressure on an object being hit by light, depends on the photon's change in momentum. We said that you have one amount of change in momentum if you absorb the photon. You have a different amount of change in momentum if you reflect the photon. So if you absorb the photon, the photon pressure on the object will be given by this, E over the speed of light times the area divided by delta t. And if the photon is reflected, you will have basically the same equation but a factor of 2. All we did was we inserted delta p from the previous slides into right in here. So the final concept I'm going to give you is the notion of intensity. So intensity of light is the average energy per unit area per unit time. So the intensity of light is the energy divided by area times time. Now, combining this definition of intensity is given by capital I, and plugging this result into what we have over here for photon pressure, we could say that if the photon is absorbed by the object, the radiation pressure on the object is I over c. And if the photon is reflected by the object, the radiation pressure on that object is 2I over c. So this is where the slides are going to end. I am going to go do 2 practice problems, and then we'll have a final thought.